So today I'd like to go a little bit further deep about multiple comparison procedures. We've seen them, we've used them, but I need to give you a bit more detail so that you see the problems a bit more under the correct perspective. Think that multiple comparison procedures are very much used in practice. So what we do is usually do an ANOVA and then multiple comparison procedures to understand which is better than which. That's the question. Which is better than which? This is the aim. You know this already, but we go through again. If the F-test in ANOVA is significant, our conclusion is that treatment effects are not all zero. If you remember the null hypothesis, the null hypothesis was that all alphas, all treatment effects were zero. So if this is false, then the opposite is that at least one alpha value is non-zero. So what we know is that there is at least one treatment effect which is not zero. And of course, this is not enough for us because we want to answer the question, which is better than which? And we do this in two different ways. These two ways are both in the book, but you don't need to study the first one. Now I'm talking to the students in biotechnology, of course. The other ones can do whatever what they want, the PhD students, I mean. So we now use the common example. We have been investigating such an example several times so far, but today we look at it in a different way. That's the mixture example. So you can start your RStudio environment now. I give you a few seconds to start. And then you need to load the usual file mixture.csv. So I'll do this now, and then you will do that and give me a feedback when you're done, please. So cleaning everything as usual. Perhaps I should make it bigger so that you can see better. Okay, that's bigger. Hope this is enough. So clean everything and load, create the file name. That is as usual. Okay, and load the file name. Right. Sorry, I forgot the positioning. All right, now it should be okay. Yeah, it is. Right, so this is the dataset, that we know so far. 4 herbicides, and the 4 herbicides treatments are composed by the unweeded control, the untreated control, and 2 herbicides alone and in mixture. And we want to control one weed that is Solanum nigrum, and the experiment is completely randomized. So we do the usual exercise and fit the ANOVA model. And put the weight as a function of treatment. First we better, that's not strictly necessary, but it might help us in some cases. We transform the treatment into a factor. So we do this before fitting the model, and then we fit the model. We do not inspect the model. That's not necessary because we did that already. And today I want to concentrate on multiple comparison testing. So giving you the code, you see two lines. First one, we transform the treatment into a factor because that's originally a character vector. And then we fit the model. So now we did this already, but we want to compare the treatments. Also Yukong is there. Did you fit the model also, Yukong? So here we go. Now, first of all, we calculate the means, the expected marginal means. And to do so, we need to load, because we have already installed it, I expect. We load the EM means library. And then treat means, we use the function EM means and pass the model object and the effect, that is treat. And we inspect the means. Here we go. Passing you is code as well. Now we need to make comparisons. So I go back to my presentation here. So we have two ways to go. First way is to set up contrasts in general. So please note the means, 9.18, 5.13, and so on. We can make contrasts, that is, we can make linear combinations of means. What do we mean? We mean that we take the four means, multiply each mean by an appropriate coefficient, and sum. This is one contrast here. So we have 1/3 multiplied by the first mean, 1/3 multiplied by the second mean, 1/3 multiplied by the third mean, then we have -1 multiplied by the fourth mean. So if you look at this contrast here, you see that there is a meaning inside. Here, in the first part, if we take this part here, let me see whether I can annotate. Here, this part here, this one. So we are summing the first three means and dividing by 3. So what we are doing indeed is calculating the mean, singular, for the first 3 treatments. So this part here is the mean for the first 3 means. So that is, so if you look back at the means here, you see that the first 3 means are the herbicides. And here we subtract the mean for the 4th treatment. So this contrast indeed is calculating the difference between the herbicides on one side and the untreated. So this contrast here answers one question. Is treated better than untreated? Okay, so I am translating my research question into a contrast. And I calculate. So what I see here is that the treated, there is a minus here, which I forgot. The treated gives 6 units, 6.4 units of weight less than the untreated. So treating is indeed effective. So that is the approach. We are translating research questions into contrasts. This is in general. However, I do not intend to talk about the contrasts here because they are not really very much used in practice, at least not in general. You will find information in the book if you would like to look at that. That is indeed very elegant. I mean, considering translating research questions into contrasts is a very elegant technique, but it's difficult and not very much used in practice. So we jump this part. And we talk about multiple comparisons, which are a certain type of contrast. So this is by contrast now. So that is a pairwise comparisons. We are comparing rimsulfuron against unweeded. So if we want to compare rimsulfuron against unweeded, I can write it as a contrast. I take the 4 means, like here, and use the coefficient 0 for the first and second mean, because these are not the means relating to rimsulfuron. These are the other means. So I use the coefficient equal to 0. And then I put a coefficient equal to 1 to the third mean, which is rimsulfuron, and a coefficient equal to -1 to the unweeded. So you see, I'm writing a pairwise comparison as a contrast. So it's still a contrast, but a specific type of contrast. right? I can have a lot of contrasts. In this case, I can have, first of all, we have two possible situations. So the first situation is that we try to do all pairwise comparisons, and that is known as the 2K approach. And second, we can compare all means against a control, or all means against the best or the worst, if you like. And this is the Dannett type. So telling you again, the 2K type of contrasts is all pairwise comparisons. In this case, we have 4 means. So it's 4 by 3 is 12 divided by 2. That is 6 possible pairwise contrasts. Or another situation, the Dannett type. The Dannett type. So we have to compare one against all the others. And the one might be, for example, the unweeded. We can compare the unweeded against the other 3. So we have 3 contrasts, not 6. So it's less in this case. Hope this is clear. Now we consider one contrast. This contrast I've been talking about, rimsulfuron against unweeded. So take rimsulfuron against unweeded. So I have to take the third mean, which is 16.86, and subtract 26.77, getting minus 991. There is an approximation, of course, inside, because the means are approximated to the second decimal. Yeah, what this is telling us, it is telling us that there is a difference between the 2 treatments, and the second treatment has a higher mean than the first one, right? So the rimsulfuron is indeed effective because it seems to reduce the weight of weeds. And of course, this is a simplified contrast because I didn't write the other means, but it's no point because we have a coefficient of 0. So it doesn't make any point to use the other means. This is just to show you that we have a type of contrast. So now we need to, it's not enough to consider the difference, because we know that this difference relates to the sample. It does not relate to the whole population. And we want to talk about the whole population, not the sample. So we need to write down the uncertainty about the population. So what do? We need to calculate. We need to calculate a standard error for the difference, the uncertainty about this difference. The first mean is uncertain. The second mean is uncertain. The difference has an uncertainty which propagates from the means to the differences. And this is what we want to calculate now. And we know the propagation of errors says that the sum, the variance of the sum is equal to the sum of the variances. So again, the propagation of errors says that the variance of a sum or a difference, it's still a sum, is equal to the sum of the variances. And what is the variance of the first mean? We are moving inside an ANOVA model, and we know that the variances are homogeneous because we have tested and checked for the basic assumptions, and we saw that they hold. So the variances are homogeneous. The best estimate that we have for the variance is this one. So we take the model and make the partitioning. We partition the variance, and we see that the residual variance is 15.35. And this is the best estimate for the variance of the whole data set. So we can calculate the variance of a mean by taking 15.35 and dividing by the number of replicates, which is 4. This would be the variance for one mean. It's 3.8375. So now that we know this, we can calculate the variance for the difference. That is 3.8375. That is the variance for the first mean, and we add the variance for the second mean, which is the same. So I could as well write 2 by 3.8375. So this is the variance for the difference. Now, the standard error for the difference, the SED, is equal to the square root of this variance. So this is the standard error of the difference. And that's it. SED 2.77. Yeah, here we go. Here in this slide, I did the same calculation, but I added all the variances for the other means, but with the coefficient equal to 0, just to show you that this is the general way to calculate the variance for a contrast. In this case, of course, I can remove this because the coefficient of 0 makes the product null. So I have a difference and I have a standard error for the difference. So I have a difference and I have the uncertainty. I'm passing you the code here, just in case you might need it. And I'm just wondering whether you're clear with such an approach. What we did was to decide a contrast, write down the contrast, and calculate the uncertainty for the contrast. That is what we did. You right with this? Or you have any questions? No questions, no doubts, all clear? So Valeria said clear. Thank you, Valeria, for your feedback. You come clear? Okay, thank you. Now, let's go ahead. So that seems to be clear. So let's make a further step. Now, what I could do is to, for example, to calculate a confidence interval for the contrast. That's interesting because it gives me the effect size. So we see that there is an effect. We notice that this is equal to minus 9.9, so almost minus 10. But we are uncertain about the real effect size, so we could calculate confidence intervals. Confidence interval for contrast, in this case for the difference. And the confidence interval, we might take a naive confidence interval, for example, by writing twice the standard error. So this tells us that the real mean goes from minus 9.91 plus twice the standard error. So, and minus 991 minus twice the standard error. So we see that the difference goes from the real population difference should be with 95% probability, should be included within the interval which goes from minus 15 to minus 4. So we see that with very high probability, the difference is negative, strictly negative, and it is non-zero with very high probability. I mean, if we repeat the experiment several times, we should obtain differences within the confidence interval. So we are pretty sure that the difference is not zero, is lower than zero, it is negative. We might also calculate a more precise confidence interval. Here we have, if we look at the set, let's look again at the ANOVA partitioning. We see that the set was calculated starting from the residual mean square, which has 12 degrees of freedom. So the set, standard error of the difference, has 12 degrees of freedom. But 12 degrees of freedom is lower than 20. So we might expect that 2 is too small multiplier. So we need a better multiplier. And we can take the 97.5 percentile from the t distribution, which is a more correct multiplier. So we take QT, a quantile from a t distribution, 0.975 with 12 degrees of freedom. And we see that the multiplier is slightly higher than 2. Not much higher, but slightly higher. So in this case, we rewrite the confidence interval like this. We replace 2 with the 97.5 percentile from a student's t-distribution. And we go here. So the interval becomes wider, but still we go from minus 3.9 to minus 15.9. So again, with very high probability, the interval is strictly negative. That means the difference presumably is not zero, likely is not zero. So this is the code to calculate confidence intervals for the contrasts. And I'm passing that to you. And here we go. And it's also written in the slide here. So that's good. Again, this is important because we have the effect size with confidence intervals, confidence limits, as it is written there. But still, we would like to take decision. And the decision is contrast different from 0. We have seen that the confidence intervals, the confidence limits, are negative. So with very high probability, the contrast is different from 0. But we want to take a decision, a yes or no decision. So we need to calculate the t-value as we did yesterday. So we take our difference. So testing hypothesis. The hypothesis is that the contrast is equal to 0. So let's use a C, a capital C. The contrast is 0. That's our null hypothesis. So if the null hypothesis is true, what we have observed is Ti, I'm using Ti in order to avoid the capital T, which is a reserved character in R, because it means true. Now I'm writing Ti. That is equal to minus 9.91 divided by the standard error of the difference. So we have Ti that is equal to minus 3.58. So we know that if the null is true, the difference should be 0 and T should be 0. But we did not observe 0. We observed minus 3.75. And we know that we observed the minus sign just because of the ordering of means, but we could have observed the 3.57 if we had reversed the direction of the difference. So we are in the range which goes from minus 3.57 downwards and plus 3.577 to above. Okay, so we have the two tails of a distribution. Is it possible to obtain such a value when the null is true? Yes, of course, it is possible because there are random fluctuations. How likely is it? We can go and check this probability in two ways, by building a Monte Carlo simulation, as we did a few weeks ago, or we can use the student's t-distribution, because we know, we have seen by using Monte Carlo simulation that the sampling distribution for T takes the form of a student T distribution. So we take the student T to calculate the probability of obtaining minus 3.577 with 12 degrees of freedom. And this is very low. It is almost 2 probabilities in 1,000. Right? So, but that's not enough, because we need to sum the probability that we obtain 3.577 upwards. So lower tail equal false. But this is the same as before. If you look at this, it's the same value. And of course, the T distribution is symmetric. So I can just remove this and take twice this value here. And that makes 0.0038. So this is my p-value. P-value. That is the probability of observing such a value here or higher in absolute value when the null is true. So what we do, we reject the null because the p-value is lower than the critical threshold of 0.05. So the p-value is lower than 5%, and therefore we simply reject the null. And we conclude, sorry. And conclude that very likely G is different from 0. So that is what we do. And it's very similar to a student's t-test, but the difference is that at the very beginning here, we are using 15.35. That is the residual mean square from the ANOVA table, because we are working under the homoscedasticity assumption. Now, the fact is that we should do this for all differences, and we do not want to do this by hand. Therefore, we use R. So, pairwise contrasts with R. And we've seen that. We take the means. Here we go, treat means, and use the function contrast. Treat means method equal pairwise. Now, we've spoken yesterday about the multiplicity adjustment, but so far we do not adjust. So we consider the 6 contrasts without thinking about any adjustment. So adjust equal no. And here we go. And here we have the 6 contrasts, and we see that the final contrast here is exactly the same as we calculated before. So I'm passing you this code here. And I'll show you that we can compare all against one by simply writing here method equal donenet. I think I need a double T. Yeah. So if I, of course, in this case, I'm comparing by default all treatments against the first in alphabetical order. That means nothing to us. So we change the reference and we compare all treatments against the unweeded, for example. That is the last one. So we write ref equal 4 because it's the fourth mean. And here we go. Now we compare all against the unweeded. So again, writing down these two types of contrasts before we go ahead, and I'll pass you the code for both types of contrasts. In the first case, it's a pairwise set of contrasts, and so we have 6 contrasts. In the second case, we are comparing all means against the fourth one, that is the unweeded. So we have only 3 contrasts. And of course, we see that the final one is the same in both cases, because we have minus 991 and we have 0.0038 as a p-value. So, any questions so far? Because now we have to talk about the adjustment with some more detail. So, do you have any question? Of course, I can also calculate user-defined contrasts. I mean, like before, taking the sum of the first 3 means and comparing with the fourth one, or I can do whatever I want. But this is the most common situation, pairwise comparisons. Good. Shall I go ahead, or you have questions? No questions. Okay, no questions. Would you like to take 5 minutes rest? Or you prefer to go ahead and we stop, let's say, 15 minutes earlier? What do you prefer? It's the same for me. No preferences. Are you particularly shy? Or you're not there, you're sleeping, or whatever? Okay, so finally got, yeah, so it looks as if a majority of people can go ahead. You are not too tired and you are not sleeping yet, at least not all of you. Okay, so let's go. So here we have all the code in the slides. Thank you for your feedback. That's very kind of you. Again, it's all the code is written on the slides. now we start discussing the multiplicity problems. We already discussed it yesterday. So we have this problem here. The problem is that with k contrasts, for each contrast, there is less than 5% error probability. And that would be the comparison-wise error rate. However, we've seen yesterday that the probability of making at least one wrong decision is much higher. That would be the family-wise error rate. Yesterday, we saw that with 10 treatments, we have a lot of comparisons, and the probability of making at least one wrong decision is close to 100%. So we are almost sure that we can make errors somewhere. In this case, we have only 6 comparisons, and there is not much a difference, really, but still there is some difference. We have a probability of making at least one wrong decision. For example, let's calculate this. I'm taking the formula here. So the formula is multiplicity problem. The formula is that if we take decision at the 5% probability level, the probability that we are right is 1 minus 0.05. And with 6 contrasts, the probability of taking at least one wrong decision is this one. That is 23%. So you see that we take decisions at the 5% error probability level, but indeed the probability that we commit at least one mistake is much higher than 5%. It is 23%. So not much higher, but higher. It's not like yesterday when we made the calculations with 10 means. In this case, we have just, oh, sorry, I wrote 5 instead of 6 here, because we have 6 contrasts. Sorry, I was thinking about 0.05. So that's 26%, even more, and of course. So this might not be acceptable. Please note that if we do not make all pairwise comparisons, but we make comparisons against a control, our family-wise error rate is lower. It's 14%. So the number of comparisons we do matters. The more comparisons we do, the higher is the multiplicity problem. That matters. Because if we want to make a correction for the multiplicity problem, here, with all pairwise comparisons, we need to be more strict than with the Dunnett type of comparisons. Right? So, how do we keep this problem under comparison? First of all, I have to tell you, and we can read the red statement together because that's very important. There is wide consensus in literature that we should always correct for multiplicity. So this is very important. If you go publish some manuscript and if you have used a multiple comparison procedure, if you have not adjusted for multiplicity, the reviewer is going to complain with very high probability because there is wide consensus that we should correct. So, in practice, we should respect a family-wise error rate, which leads to strong protection against false positive errors. But please consider that if we increase our protection against false positive errors, at the same time, we decrease our protection against false negative errors. So we are less likely to commit false positive errors, but we are more likely to commit false negative errors. This is important because we need to keep such a balance into consideration. Please remember the Popperian principle we spoke about at the beginning of the course. The Popperian principle says that with experiments, we can only reject hypotheses. We cannot organize experiments to accept hypotheses because we have no way to demonstrate that an hypothesis is true, because a future observation might lead to rejection. But we can organize an experiment to prove that an hypothesis is false by rejecting it. If we show that the hypothesis is false, then it is false. We have rejected it, and once it is rejected, it is rejected. So, according to the Popperian principle, we need to adopt a strong protection against false positive errors. And that's the orientation in statistical methodology, experimental methodology. I'm not saying that this attitude is correct or not. Okay, but that is the nowadays attitude. I don't know whether it's gonna change in the future, but so far we organize experiment to reject hypotheses, and we need to adopt strong protection against false positive errors, which leads us to adopting corrections for multiplicity. And how do we do? We have several types of corrections, but we just see a few of them. The first one is the so-called SIDAX correction. That's the easiest one, because we adopt such inequality here. So, for example, let's take this p-value here, 0.0038. This would be the comparison-wise error rate. We transform it into a family-wise error rate by using such an inequality. I simply write here 0.0038. That's the incorrected p-value, and correct it like this. So you see it becomes higher, but it is still significant. And of course, with the other Garnet type contrast, the correction is different. Oh, sorry. 0.0038. So you see that the p-level is changing less in this case. So if we want to do this, we simply use the same code here, and instead of writing adjust equal none, we write adjust equal SIDAC. And we get the adjustment here and also here. What is the consequence? I think we should take a look at both the methods. Here is without correction. Here is with correction. Let's look at this one with the other together. Look at this contrast here. So that is metribuzin against rimsulfuron. In this case, if we do not adopt any correction, the contrast is significantly different from 0. But if we correct, this is no longer significantly different from 0. So you see that we are losing significance. We have a lower power. So we decrease our possibility of committing false positive errors. That's it. I'm not really, I don't want to go strictly ahead with this. Another possibility is to use the Bonferronis correction. We use a difference inequality, which is simply, we take the uncorrected p-value and multiply it by the number of contrasts. That's the Bonferroni correction here. And we see if we adopt the Bonferroni correction, let's take this one and adopt the Bonferroni correction. And we see that we are even more conservative, because we had here for the second contrast, we had 1.6% at the beginning. Then we jumped up to 9.7%. And again, here we jumped even higher at 10%, 10.1%. So we see very protective here. Both methods are very conservative. So we need to be careful. We are increasing our possibility of making a false negative error. Right, so we are running the risk of saying that a contrast is not significant when it indeed is. Well, we need to say that with R, there is another possibility that is to use the single-step procedure. The single-step procedure uses the multivariate t-distribution to adjust the p-value. And we will not talk about this in detail because it's rather complex. We only have to know that using such single-step procedure implies that we keep all the correlations into consideration. And the contrasts are correlated among each other because they use the same error. So they are correlated. And we need to take that correlation into account. And if we take that correlation into account, we can make an adjustment which is more precise and less conservative. And that's the way we do. So it is the default method in R, and it's okay in 90% of the cases. So we just need to know this. We make the comparison and adjust by using the default method. And here we go, we are, for the second contrast, 6.97%. So we are slightly lower with respect to the CDAC and Bonferroni's corrections. Here we go. And that's the default procedure. Of course, we can translate this into a letter display. So, letter display. We use the function, so we need to load the library multcomp and use the function cld, passing the means and saying that we want to use capital letters. And first of all, we do not adjust so that we can see the difference. So here we go. And then second, we adjust. So we remove this and use the default adjustment. And here we go. And now we take a look inside. So, hope you're there. Look at the first one here. We see that we have AA, so which means that the first two means are similar, not significantly different. Then both means are different from rim sulfur. And all means are different from the unweeded because they have different letters. If we take a look at the second, it's giving us the information here. We have used a 2K method. So because that's a 2K contrast and we have food protection for 2K contrast. Here we see that something has changed because the mixture and metribuzin are not significantly different, but now metribuzin is not significantly different from rim sulfuran. So this contrast here is not significant. So something has changed, and we noticed that before. So I think you have not much to tell you further. We can make another exercise now. So yesterday we have done the exercise 2. We have done the exercise 4 yesterday. Today we do the exercise 3. And I'm copying the data, inputting in my R console. So that would be the exercise 3, copying the table. Here it is mixed, so it's let me see what can I do. Perhaps I should take not good copying from here. So let me take another way to get the data in and do this in a short time. Here we go. Now, here we go. 3.3, 3.4, here we go. And take this one, which is much better. All right. Perhaps can do it even better and do like this. Copying this first and copying this second. All right. So now this is the temperature. Putting commas here. Commas. And closing here. Now I'm taking this, sorry, made a mistake here because I forgot one comma here. Taking this, and then I'm passing you this, edit temp. Here we go. So this would be the temperature. Oops. And here we go. This is the temperature. And here we go. Then I have the hours. Here I put the commas. And close here, load, and edit hours. And here we go. Here we go. And here you have the hours. So what is that? Let's look at the, here we go. Let me do it bigger. The exercise is this: the failure time for a heating system was assessed to discover the effect of the operating temperature. So we made an experiment with 4 operating temperatures with a heating system. We had 6 replicates and measured the number of hours before failure. So that means we need to find which temperature gave the highest number of hours before failure. That's good, because if the heating system failed later, that means it is better than failing before. So we need to find the temperature which corresponds to a high number of hours before failure, because that's certainly better. So we made an experiment to discover, because we operated with different temperatures and measured the number of hours before failure. What is the best what is the best temperature? What is the best operating temperature? So now we do this exercise. But before we start, I'd like you to feedback whether you managed to input the data. So clearly we can clear everything at the beginning and then input the vectors. So please advise when you're ready to start. So as long as you proceed, you can go ahead by yourself. So what do you have to do? You have to fit an ANOVA model, check the model. If it's necessary, you have to transform. And finally, you have to compare all temperatures. So try to go ahead by yourself. I'll give you a few minutes to go. Is that okay? So it's 10:03. Let's say that you can go ahead until 10:08, so 5 minutes. So your task is to fit a model, inspect the model. 3, you need to transform if necessary. And 4th, you need to compare the temperatures to assess the best one. I'm just telling you something which is important. The temperature is a numeric variable. And we strictly need to transform it into a factor. Otherwise, the model is wrong. So let's do this together. We take the temp and transform into a factor. So we need to do this. That's very important. Otherwise, if you do not do this, the model is wrong. So try to go yourself and do the exercise. So this is what you have to do. And I give you 5 minutes. Then we do this together in 5 minutes. If you have questions while you do your job, I'm here to answer you. So did you manage? Anybody manage to do that? One partial minute. So let's do this together now. So first we fit the model. That's using this usual function where we put the hours as a function of temperature. Temperature is a factor. Then we inspect the model fit. Plot a model object which equal 1. So we see again that there is a funnel shape here, so not random at all. Variances are not homogeneous here. This is really important. Now we can also make the second plot, the QQ plot. And we see that data are skewed. That's clear. So the situation is pretty clear. Here we have a quantitative variable, that's the number of hours, but nevertheless, we have clear signs of heteroscedasticity and the residuals are not Gaussian. So we need to take an action. And what action do we take? We transform. So we load the library mass and use the Cox function to see what transformation is necessary. So that's unusual situation. The highest likelihood value here corresponds to a lambda which is included between 0 and -1. So, but confidence intervals go from a little bit less than -1 to almost 0. So what transformation, what understandable transformation can I take inside this interval here? I take -1 because that's the reciprocal transformation, which is understandable, quite often used. So what do? I refit the model, mod 2, taking the inverse of the number of hours in place of the number of hours and put it as a function of temperature. And here we go. Now let's do the ANOVA partitioning. And here it is right. So we have 3 degrees of freedom for the temperature because we have 4 temperatures. We have 4 temperatures and 1, 2, 3, 4, 5, 6, 2, 4, 6 replicates. That would be 6 by 4, 24 data. So the residuals is 20 degrees of freedom. 20 plus 3 is 23. That's the total number of degrees of freedom with 24 data. 24 minus 1 is 23. And you know that. So we see that the difference between temperatures is very highly significant. So we have very negligible error probability of false positive. We reject the null, and we are pretty. Our data support such a rejection pretty well. So now we need to decide which temperature is the best. Let's look at the means. Mean temp. Let's take the expected marginal means, which are equal to the arithmetic means in this case, because the experiment is fully balanced, because we have the same number of replicates. So, mean temperature are obtained by using the EM means function, passing mod 2. Be careful, I have to pass mod 2, which is the right model. Now I do not even need to transform back, because I'm not really interested in the number of hours. I'm just interested in knowing which temperature gives the highest number of hours before failure. So I do not really need to know the number of hours. I don't mind. So I just put now as a function of temperature. And here we go. We see the means. Mean temp. So the expected marginal mean is the reciprocal. So I don't need to look at that. But I see that the highest, well, this is a reciprocal transformation. So I need to understand that the lowest value, the highest the number of temperature, because it's a reciprocal transformation. If we look back at the original means, let's calculate the arithmetic means so that we understand our supply. Hours, temp, mean. We see that indeed the highest number of hours is obtained with 1520 hour temperature. So it would say that this temperature is the best one because it saves the heating system, which can function without failure for a higher number of time. So here, this is the best. So now we have 4 means. If we make all comparisons, it would be 4 by 3 divided by 2. That is 6 contrasts. But we don't need to make all comparisons because we need to compare. We just need to compare 15, 20 with all the other temperatures. That would be comparison with the best. And that's interesting. So how do we make a comparison with the best? Well, we can do like this. Sorry, that's not interesting. Contrast. Take the means, mean temp, and method equal time length. And we make an adjustment for multiplicity. Now here we have a problem. It's relating to some sort of, just simple problem. I forgot the double T. I thought there was non-compatibility, which happens now and then, but that was not the case. So what do we see here? We see that the first contrast, so 1620 and 1520, is not significant, while the other contrasts are significant. So how do we conclude? We conclude that the best temperature is the lowest one, but the second one, 1620, is not significantly worse than the first one. So this is our conclusion here. And we have a way to decide. And that's it. So I'm just wondering whether you have, perhaps I should pass you the code to solve the problem over the chatbot. And if you have questions, just do them, ask them. Otherwise, I'll see you tomorrow. Thanks for your attention.